Hi, welcome to lesson 17a, Kinematics. The goal of today's lesson is to learn how to use calculus to solve problems involving motion in a straight line. So the first thing we need to sort of get out of the way is a little bit of terminology. And there are differences between words like displacement and distance. So displacement is basically a vector quantity. Displacement is the movement of an object from one place to another. Therefore, displacement, going from one place to another. And distance is the total distance traveled. So displacement, being a vector quantity, will have a sign to it. So it could be a negative or a positive depending on the direction of motion. And being a vector, displacement will have a magnitude and, like I said before, a direction. So if I'm looking at displacement, I could say that the vector could be like this, and the direction, or the sign of it in this case, is going to be positive because it's going to the right, and this length of it is the magnitude. Okay, so we've got a couple of things going on here when we talk about displacement, being direction, the positive part here, and the magnitude, the length of the vector. Distance is just a magnitude. It's just a scalar quantity. So if we take a look at this very well drawn stick figure, let's say this is like the bird's eye view of a hallway up, it doesn't matter exactly what floor it may be, but some hallway in a school perhaps that goes around. There's all kinds of classrooms off the hallway. Here's one open door here. If we look at the displacement of this person from the center of the doorway, we can see, actually we'd not talk about the angle there, but we can just talk about the horizontal distance from the doorway. We can see, the displacement. The displacement from the doorway, we can see that it's negative, and the magnitude, the length of that vector, isn't very long. So this person is a very short negative distance from the doorway. That would be the displacement. What we don't know is perhaps if the person started at this doorway, we're going to use this doorway as O, the origin perhaps, or the point of reference. We don't know, looking at this displacement from that point, how many times or where the person may have walked. That person may have walked around once, may have walked around 2 times or 3 times. It doesn't matter how many times, but we don't know how far they walked around there. So if that person did walk around, let's say at least once, and perhaps this is a 30-meter hallway here. Of course, this would be 30 meters here. Let's say this is, just for sake of simplicity, 10 meters and 10 meters. So we would say that the displacement of this person at this moment in time, let's say, is negative 2 meters. That would be the displacement of that person from this point. The distance that the person may have walked would be, well, all of this distance here, plus that 10, plus this 30, plus that 10, plus all the way back to here again. So in total along this hallway, they would have walked, say, 28 meters, because they're 2 meters away from this point of origin. So there's 28 meters, plus this 30, plus the other 210. So that would be 48, 30, 78 meters. So the distance walked would be 78 meters. The displacement that this person is from that point of origin would be negative 2 meters. Okay, so that's just a a bit of terminology that we need to discuss in terms of looking at kinematics and movement. And when we talk about velocity, again, velocity comes from displacement. Okay, so the velocity is the rate of change of displacement over time. Speed is the rate of change of distance over time. Okay, so we can look at average speed or instantaneous speed. The speed is actually the absolute value of velocity. Okay, in such that we're not regarding the direction of motion when we're talking about speed. We're just talking about the actual speed. Whereas velocity, we're looking at speed and the direction of motion. Okay, so there's the difference between speed and velocity there. Okay, so when we look at velocity, for example, if we know that the displacement, and usually it's noted as s of t, so the displacement s of t, then if that's the case, then the average velocity can be calculated by the position at time t2 minus the position at time t1 divided by the difference in those two times. So that's how we would calculate average velocity. If we look at instantaneous velocity, well, instantaneous velocity, we can use v of t as that notation. Well, that's the first derivative of the displacement function. So it's the gradient function of the displacement function, or the first derivative. And when we look back at first principles of the gradient function, the first principles of this derivative of s of t would be s of t plus h minus s of t all over t plus h minus t. So remember that h is that horizontal distance between or away from a specific time value that we're looking at, and s of t plus h is the displacement at that specific time. Then we would subtract that from, or we would subtract s of t from that and divide by t plus h minus t. The two t's would of course cancel. We're just left with over h. Okay, so that's the limit definition of the derivative. In this case, we're now applying it to velocity and the rate of change of displacement. Okay, so we're also going to move along and do the same sort of thing with acceleration. And acceleration, if we look at average acceleration, that's found when we take the velocity now at time 2 and we subtract the velocity at time 1 and we divide that by the difference between the two times, time 2 and time 1. And then, so that's the average acceleration, and then the instantaneous acceleration, well, that is denoted as a of t, and that's the same as the derivative of the velocity function. And by the way, this is actually also the second derivative of the displacement function. And so the derivative of the velocity function is then, of course, using the same notation as before, the limit definition, the limit of the velocity at time t plus h minus the velocity at time t divided by the difference between t plus h and t as h approaches 0. Okay, so that's how we would define the acceleration, or the instantaneous acceleration of some object or some particle. Okay. Now, one little thing that we will take a look at are some signs and the significance of some of these signs. So, when we look at the the signs of the displacement function. Well, if the displacement function is equal to 0, then that means that the point, this object or this particle, because usually we use the word particle so that the object that we're referring to doesn't have any size or mass or anything to kind of get in the way of the interpretation of the exact point where the object or the particle is located. When it's equal to 0, then the particle is at the origin, at this reference point O. If the displacement function is greater than 0, then the particle is located to the right of 0, because remember, this is a vector quantity, so if it's to the right, it's going to be positive, which is greater than 0, so the particle is to the right. If the displacement function is less than 0, it's going to be negative, therefore the particle is located to the left of the reference point O. When we look at the signs of the velocity function, well, if the velocity function is 0, then we know that this particle is instantaneously at rest. So right at that split second or fraction of a second where the velocity is 0, then we know that the object has stopped moving. If the velocity function is greater than 0, the particle is moving to the right, and if the velocity function, the particle is less than 0, then the particle is moving to the left. So if an object is moving to the right and then all of a sudden starts moving to the left, right here where it changes direction, that's when the velocity is equal to 0, because it has to come to rest momentarily in order to change directions. Okay, so it's going in some direction, it stops very briefly and then turns around again. So that's when the velocity function equals 0. Okay, when the particle is instantaneously at rest. So as we saw before, the velocity, the instantaneous velocity, is the limit as h approaches 0 of s of t plus h minus s of t all over h, because the two t's have cancelled already. So if the velocity function is greater than 0, then that means this whole thing has to be greater than 0, which means, and h is going to be a positive value, s of t plus h minus s of t. So if the whole thing is greater than 0, meaning the velocity is greater than 0, that means that the numerator has to be greater than 0, which means that s of t plus h must be greater than s of t. And if that's the case, then here's the position of s of t, the position of the particle at s of t. Here's the position of the particle at s of t plus h. Therefore, we know that the particle has moved to the right. Okay? So therefore, p is moving to the right in that case. When we look at now acceleration, if the acceleration is greater than 0, the velocity is increasing. If the acceleration is less than 0, we know the velocity is decreasing. So if the acceleration is positive, velocity of the object is increasing. If the acceleration is negative, then the velocity is decreasing. And if the acceleration is equal to 0, then the velocity will be constant. It may be a maximum or a minimum value. And then here's a bit of a useful table for us in terms of phrases and phrasing. So in initial conditions, well, initial means at the beginning, so time is 0. We don't know necessarily about these things, but we know for sure initial conditions time is 0. At the origin, we know that the displacement is 0. If something's stationary, then we know the velocity is 0. So like I said up here, if it changes direction, right at that spot where it changes direction, it has to be momentarily stationary. Therefore, velocity is going to be 0. And what I just pointed out, if something reverses direction, the velocity is going to be 0 at that point. Okay. Maximum or minimum displacement, again the velocity will be 0, because at that point, like I'm showing here, the velocity in this direction is positive, the velocity in this direction is negative. Therefore the velocity must change signs, and so at a maximum or minimum displacement, the velocity changes signs in order to turn around. And that would then of course correspond to a local maximum or local minimum distance from the origin. Constant velocity, the acceleration is going to be 0 because it's not increasing in velocity or decreasing in velocity. And maximum or minimum velocity, again the acceleration is going to be 0 because it's going to be constant velocity if the acceleration doesn't change. So if it's a maximum or minimum velocity, we would need a sign diagram to kind of figure out what is actually being, what the velocity actually is at that maximum or minimum. Okay, and of course, because it's a max or min, it's not changing. Therefore, the acceleration is going to be 0. Okay, so we're going to take a look at a couple examples tomorrow in class. And in the meantime, what I would like you to do is I'd like you to go to go to the textbook on page 416 and look at example 1. Then quickly look through questions 1, 3, and 4 on page 417 to kind of see what kind of questions will be asked of you. Then on page 420, go through example 2 and ask the self-tutor to explain things to you so you have a full understanding of that material. And then take a quick look at questions 1, 3, 4, 5, 7, and 8 on page 421 before you come to class tomorrow, before we do our examples together. So thanks for watching, and we'll see you in class.